Okay, thank you for the introduction, and thanks to the organizers for the opportunity to speak here today. It's very nice to be back at an in-person conference after so long. I'm going to talk today about how we can use topological machine learning techniques to analyze various condensed matter systems, and in particular to detect phase transitions which may be difficult to pick up using conventional machine learning approaches. Okay, that's the point. Okay, so since this is the first talk at this conference focusing on machine learning, I thought I'd start with a bit of a pedagogical introduction to why machine learning shows some promise for the better understanding of condensed matter systems. Then I'll give a similar introduction to one particular machine learning technique, which is persistent homology, which can be used to learn topological features of your system of interest. And then finally, as an example of how persistent homology can be used to analyze phase transitions, I will consider localization transitions in a simple toy model, a generalized Aubry-Andre-Harper model. Okay, so broadly speaking, machine learning refers to a variety of algorithms which use data to build models to perform various tasks. So a very simple example of this is regression type algorithms, where the aim is to find a function which can fit your data points. So nowadays there's quite a vast zoo of machine learning algorithms that are being developed. For us as physicists, what is probably of most interest are the two classes of machine learning algorithms known as supervised learning and unsupervised learning. So supervised learning can be considered as analogs of regression type problems, where we want to build a model which is able to make predictions or extrapolate from labeled data sets. So this includes applications such as curve fitting, forecasting, and image recognition. On the other hand, unsupervised learning relates to algorithms which are aiming to find patterns in unlabeled data. So this includes algorithms for clustering, reducing dimension to identify important low-dimensional subspaces, and also various anomaly detection techniques. So I think from the theoretical point of view, the unsupervised learning algorithms are more interesting for us because they are aimed at sort of identifying interesting features in complex systems or grouping data into different classes. And so these can reveal new features of the system of interest. So there's a few examples of these unsupervised learning algorithms. So one is clustering. So here the aim is we have some data. This could be measurements of our system of interest. We want to group this data into different clusters. So one way this can be done is using this k-means algorithm, which is an iterative algorithm where we randomly assign cluster centers. We assign points to the nearest center, and then we recalculate the center and iteratively repeat this until we get convergence of our data into different groups here. Then if we make new measurements after this, we will assign the new measurement to the class according to where it falls, in which color region. Another important class of unsupervised learning algorithms are dimensional reduction techniques. So here the aim is to give or to obtain a faithful lower dimensional representation of your data. So here is one example where you have now a cloud of points. This could be measurements in a two-dimensional space, which have some distribution you see here. So you'll see the points are not uniformly distributed in this space. Rather, they exhibit some kind of concentration along this curve. So in fact, this reflects some hidden lower dimensional structure of the system. So what we would like to do is find this, identify cases when this occurs, because generally for analyzing data, it's much easier to deal with like 1 or 2D data than much higher dimensional systems. Okay, so that was a very brief introduction to some machine learning techniques. So now I'll talk a bit about why this is interesting from the point of view of topological quantum matter. So actually, in the literature over the past few years, there has been growing interest in applying these kinds of techniques to detect phase transitions, including topological phase transitions, in various models of condensed matter systems. So how does this work? So the first step in any kind of machine learning problem is, first of all, you need to identify what your input data is. So in this case, for our purposes, the input data could be the eigenstates of your model system. It could be the Hamiltonians themselves, or even wave functions obtained from some kind of like quench type situation where you prepare your system in some equilibrium state, rapidly change the Hamiltonian, and then observe the resulting dynamics. For the case of identifying or detecting phase transitions, we would draw this input data set from an ensemble of different model Hamiltonians or model systems. Once we have this input data, then we need to identify a suitable similarity measure for comparing the data drawn from different systems. So one example from this earlier Nature Physics paper. In this paper, they were analyzing phase transitions in a classical XY spin chain. So in this case, the data set corresponds to ground state spin configurations, which are illustrated here for a ferromagnetic phase and some kind of spin wave phase. And so in this case, one natural choice of similarity measure might be the overlap between different spin configurations, which is given by this dot product between the spins. So once you have these two ingredients, so the input data and your distance measure, then this can be readily fed into existing machine learning algorithms. So in this work, the authors first performed a dimensional reduction, which allowed them to map these spin configurations to a lower two-dimensional space containing the key features. And in this lower dimensional space, what we can see clearly is that the two phases, the ferromagnetic phase and the spin wave phase, are clearly separated. The final step is then to, I guess, quantify this separation by performing some kind of a clustering algorithm, such as k-means, which allows you to detect that the data points are drawn from two distinct classes. So that's how it works, at least in theory. So in practice, the identification of a suitable distance metric for your data is not such a straightforward problem. And in fact, the results of these machine learning techniques can be quite sensitive to the choice of metric, which is discussed in this PRB paper from a few years ago. So in this case, the input data are the eigenstates of a type binding model of a two-dimensional insulator. So these are, each point corresponds to the block functions of a band. And then we draw from different model parameters, which we draw from different phases, so different phases with different Chern numbers. So if you use the standard Euclidean distance to compare these different data points, you get the following distance matrix, which is smoothly varying and does not exhibit a sharp contrast between the different topological phases. On the other hand, the authors showed here, if you use a different metric, which is this Chebyshev distance, which is basically the P infinity norm, or the largest difference between elements of your data vectors, you get a very strong contrast between the different phases. So each red region here is indicating similarity between points drawn from the same topological phase, and then we have 4 distinct phases here. And the reason why this modified metric it's much better is because it is more sensitive to the band inversion which occurs when you have a topological phase transition, whereas the Euclidean distance is capturing all this, or is biased by all this irrelevant information coming from eigenstates which are not participating in the band inversion. So yes. Sorry. So in this case, this is just so I think they are sweeping the Dirac mass of this model. So as you tune the mass, which is between these different values, which are indexed by I, you sort of tune through one band inversion, then another band inversion. So it's just a labeling for one of the model parameters. Okay, so the reason why we have this kind of sensitivity to the choice of metric, I guess, can be understood as a kind of a curse of dimensionality. So when we deal with these lattice systems or strongly correlated condensed matter systems, we are dealing with a large space of model Hamiltonians or a large space of eigenstates. Often we can't sample this. We can't perform very dense sampling of these high-dimensional spaces. And so this gives rise to a curse of dimensionality where it becomes difficult to quantify distances in this space. I like this illustration from a preprint from a few months ago, which was not about machine learning, but I think it's still quite striking. So here in this figure, this is plotting 2-dimensional projections of d-dimensional hypercubes. And the color coding is illustrating what fraction of the volume of the hypercube is contained within a spherical, within a sphere. And so in low dimensions at least, the sphere provides a reasonable approximation for the cube. But as we increase the dimension of our system, or of our space, the volume ends up being concentrated in these very thin, but very many tendril-like regions. And so as your dimension increases, actually you get a vanishing overlap between the hypercube and the hypersphere. So this challenge of this curse of dimensionality is one motivation for exploring machine learning techniques which are not so sensitive to the geometry of your space, but rather aim to pick out directly the topology of your data distribution. So this allows us not only to carry out machine learning using sparse data in high-dimensional spaces, but it also brings with it hopefully some form of robustness to noise and deformations of your input data set. One nice example of this is this PRL a few years ago, which is also focused on machine learning of topological phase transitions of type binding Hamiltonians. And here, to overcome this curse of dimensionality, the authors construct a distance metric which takes into account the potential for smooth deformations of your Hamiltonians, which preserve the band gap of your system. So my focus today is going to be on a class of algorithms known as topological data analysis, where the idea is to represent these data sets formed by point clouds in terms of some graph or a higher dimensional generalizations of graphs known as simplicial complexes. Once we reduce our data to a graph or a complex, then we can quantify its shape by computing well-known graph topological invariance. So this kind of pipeline is illustrated here, where we have a cloud of points which is sampled from the surface of a hand. And then the aim is to reduce this complex point cloud into a simpler kind of graph representation which captures the main features of its shape. Okay, so then the basic ingredients we need is how do we construct a graph from our point cloud. So the simplest way is if we consider our data points as vertices of our graph, then we can connect any pair of points which are sufficiently close together as quantified by some suitable distance measure by an edge, like so. So doing so, we can convert our point cloud to some graph. There also exist high dimensional generalizations where we also include not just edges but also triangular faces which are spanned by triplets of points. So we can construct a complex by including these faces and even higher dimensional volumes and so on, provided that our points are sufficiently close together as judged by some suitable distance measure. So the topological invariants which can be used to characterize graphs and simplicial complexes are known as Betti numbers. And so the kth Betti number is counting the number of k-dimensional holes or k-dimensional cycles in your complex. So for example, the 0th Betti number is simply the number of disconnected components. So the number of distinct sectors which can be reached by traversing edges of your graph. So here we have 3 distinct components, whereas on the right here, everything is connected. Likewise, the first Betti number is counting the number of non-contractible one-dimensional cycles. So what I mean by non-contractible here is that if we have a cycle which encloses a face, then this cycle can be contracted to a point and removed. That's why in this case the first Betti number is 0. Whereas on the right-hand side here, there is no face inside here, so this cycle becomes non-contractible. In fact, we have 2 non-contractible cycles, so the first Betti number is 2 in this case. And this can be generalized also to higher dimensional Betti numbers, which will describe objects such as voids and so on. Okay, so if you've been paying attention, one thing which I've glossed over is that this construction of the graph or the complex will obviously be quite sensitive to what kind of cutoff scale we use to determine whether to connect a pair of points. If this scale is too small, then each data point will be isolated. So we'll just have a cloud of points with no edges, no faces. As we increase this distance scale, nearby points will start to become connected. and eventually there will be some characteristic distance scale or range of scales over which our graph or our complex will reproduce the large scale structure seen in the point cloud. So we don't know beforehand which scale to pick, so the solution is to compute these Betti numbers, these topological features over all possible cutoff scales. This can be done reasonably efficiently, and this information is usually summarized in a graph form in terms of this kind of persistence diagram, where each point corresponds to a distinct topological feature of your point cloud. The horizontal axis is illustrating the scale at which this feature appears, and the vertical axis, the scale at which the feature is destroyed. So this is, for example, the persistence diagram obtained for this kind of two-dimensional point cloud. So you notice a few things here. So in the persistence diagram, the features which are at the top left, these are features which persist over a wide range of length scales. So these are the features which are typically the most robust to noise and perturbations. These are the features which are typically capturing the overall shape of the data. And so in this example, we have one cluster and one cycle, which is indeed matches what we see. On the other hand, we have a lot of features which are very close to the diagonal, meaning that these features appear and then disappear very closely. So they are very sensitive to the choice of the length scale, and therefore they are quite sensitive to noise. So even though these features are noise-induced, they are still useful because they allow you to carry out some kind of statistical analysis of the topology of your data. So to give you, for example, confidence intervals as to how meaningful these more persistent features might be. So here's another example where we have a cloud of points drawn from just a Gaussian distribution in 2 dimensions. In this case, there are no cycles. So we see all the one-dimensional features here, which are in orange, have very low persistence, and they're merely induced by noise. In the second example, with this kind of figure 8 point cloud, we have 2 highly persistent one-dimensional features, which captures the 2 cycles present in this point cloud. So this gives us a way to detect in an unsupervised manner, I guess, the topological features of your data and also the scales at which they appear. Okay, so that was all quite an abstract introduction, but this also has some applications to physics which I think are quite interesting. Interest in this topic is now growing, with several papers published in the past few years. Applications so far have fallen into the areas of using these persistence diagrams to detect phase transitions in various systems, to classify many-body entangled states, and also to characterize nonlinear dynamics in nonlinear Schrodinger systems. So the basic approach in all these studies is, once you've defined a suitable input data set, you can compute the persistence diagrams for different system parameters. Phase transitions will be associated with qualitative changes in the persistence diagram, and this can be some cases further simplified in terms of some simple summary statistics, such as the mean squared lifetime of all these features, which will change suddenly in the vicinity of a phase transition of your system. So I don't have time to go into all these different studies. I'll just focus on one early example of this approach, which was applied to characterizing amorphous materials. So in this case, the input data which is used by persistent homology is simply the positions of atoms of your material obtained using molecular dynamics simulations. And then we're using this topological data analysis pipeline in order to characterize the shape of this three-dimensional crystalline structure. So here we have the corresponding persistence diagrams. So in the liquid phase of this system, you have no kind of no order, so you get a random looking distribution of feature birth and death scales. On the other hand, in the crystalline phase, you see all the feature birth and death scales are clustered around a few critical scales, which correspond in fact to the bond lengths in this crystalline phase. What's interesting is that even in the glassy phase, in which you don't have any long-range order, but there is short-range order, this short-range order can be visible as some form of clustering of the feature birth and death scales. And if you look at the generators of the corresponding cycles, this will capture some of the short-range order, the short-range arrangement of the atoms in the intermediate glassy phase. So we were interested in how this topological machine learning technique may be able to capture the topology of eigenfunctions of topological bound insulators. So in this case, our input data set is the block functions of a band of our largest Hamiltonian. We obtain a point cloud by sampling different momenta in the Brillouin zone. Then for the block functions, a natural measure of distance is this quantum distance, which will measure the similarity between the block functions drawn from different k points. So equipped with this data and this metric, you can use persistent homology to identify the high persistence features of these block functions and thereby distinguish topological phases from trivial phases. So this was also combined with machine learning approach, I think machine learning based clustering by Professor Young and collaborators in this work. And they showed that you can go beyond this detecting phase transitions of the simple SSH model and also classify more complicated two-dimensional models, distinguishing different churn numbers. Okay, so in the last 10 minutes or so, I'd like to now discuss in a bit more detail how we can apply these techniques to study localization transitions in a simple toy model, which is an Aubry-Andre-Harper model, which is this nice model of localization in one dimension, where if you tune the strength of a quasi-periodic potential, you can induce a transition between extended and localized eigenstates. So actually we'll consider this a generalized Aubry-Andre-Harper model, which involves a quasi-periodic modulation to both the on-site potential and to the coupling between neighboring sites. So this model was introduced in this earlier paper, and it has this nice phase diagram where you can see that by tuning the quasi-periodic modulation strengths V2 and V1, you can realize three different phases, an extended phase, a localized phase, and a critical phase. In this work, the different properties of the ground state eigenfunctions could be summarized in terms of this eigenstate measure, the inverse participation ratio, which is measuring the number of strongly excited sites. So we were interested in seeing whether this kind of phase diagram could be reproduced using persistent homology. So in this case, as our input to this topological data analysis pipeline. We take the ground state eigenfunctions of our system. So here you have examples of the ground state eigenfunctions in each of the three phases. Here we have the corresponding persistence diagrams, which you see, okay, they look like they have there is some qualitative difference between them in each of the three phases. So to measure this difference more quantitatively, we can introduce different summary statistics. So first here we have, on the left is the usual phase diagram computed by using the inverse participation ratio of the ground state eigenfunctions. So you see three phases. Okay, in fact, the critical phase is not so easy to distinguish from the extended phase because both eigenstates are not very well localized. And here you have the phase diagram obtained using persistent homology, where we compute the mean squared lifetime of the features. And in fact, this looks very similar to what we obtained for just the IPR. Another measure we can consider is the entropy of the eigenstates. So here's on the left we have the standard approach, where you just compute the entropy of your ground state eigenfunction. We get some separation between the three phases. We see a similar kind of contrast if we use the persistent entropy of the entropy of the persistence diagrams. So far this was just measures computed for a system with a fixed size. We can also look at the finite size scaling of these observables to obtain the fractal dimensions of the ground state eigenfunction. And so for both pairs of measures, the persistent homology measure can reproduce quite nicely the fractal dimension obtained for the using the standard measure, such as the IPR or the eigenstate entropy. Okay, so those of you who are still awake will be asking if all this complicated persistent homology framework simply reproduces the results obtained using tried and tested standard measures, why should we bother to introduce all this kind of complicated framework? So there is actually something where we can do or find new things using this persistent homology approach. So I come back to this phase diagram based off the entropy of the eigenfunctions, or the entropy of the persistence diagrams. And so you see that the persistence diagram entropy has this dip along this line in the parameter space. So when we saw this dip, we were quite surprised as to what was causing this. So as a first step, we thought, okay, let's look at what the eigenfunctions look like along this line. And so if we plot the low energy eigenfunctions along this line, you see they take this quite simple standing wave form, suggesting that even though we have this non-zero quasi-periodic potential, these eigenfunctions don't feel this disorder at all. If we look also more carefully at this line, we find it's given by this relation between V1 and V2. So armed with these two numerical observations, we returned to the original type binding Hamiltonian and obtained an effective Hamiltonian for low energies. And we see indeed that for the low energy modes, if your diagonal and off-diagonal modulations satisfy this relation, then these two quasi-periodic modulations cancel each other out perfectly. So in effect, in this model, the disorder potential becomes transparent to the lower energy modes. Since the disorder disappears and we get these highly ordered looking eigenstates, this order is captured by this low entropy of the persistence diagram along this line. This feature is, however, missed by the eigenstate entropy, which is only measuring the distribution of your eigenstate amplitudes and is insensitive to the finer structure, to the finer shape of the eigenstates. Okay, so I'm running to the end. So the key point here is that why we're excited about this result is that it shows that using these kinds of quite sophisticated topological machine learning techniques, it is possible not just to reproduce what is already known, but it can also uncover novel features of systems which may be difficult to understand using more standard methods. Using this approach, we were able to identify this anomaly in our model phase diagram, which led us to go back, re-examine the original Hamiltonian, and come up with an analytical understanding for what was happening. So for this reason, we think that these persistent homology-based techniques could be an interesting new tool for carrying out analysis of theoretical models and experimental data. So far, we just considered the simplest non-interacting type binding models, but of course, these techniques will probably be even more valuable when dealing with interacting systems where you have to deal with a very high-dimensional Hilbert space, and traditional visualization or characterization methods don't work very well. So this is one area we're currently looking at. And of course, due to space or time constraints, I couldn't really go into much detail into topological data analysis, but there are many more techniques which are adapted to different classes of systems. If you want to know more about this area, I'd recommend these 3 review articles which are all aimed at a physics audience, so they are quite accessible. So with that, thank you for your attention.
Okay, thank you very much for the very interesting talk. So now the talk is open for question or comment.
So I'm trying to understand this audit line. Can I think of it, if I have this quasi-periodic potential, but I just look at the low energy part of my quasi-periodic potential, and it actually looks translation invariant?
Let me go back. Do I have the... Yeah, so... Yeah, so if you Fourier transform, look at the low energy modes, then yeah, you get decoupling of the momenta. So you get an effective translation invariance, but only for the lower energy modes. The high energy modes are still disordered.
But can I understand it just visually by inspecting the potential at the bottom?
As in you can't see it from looking at the disorder potential itself, because the disorder is non-zero, and so it's more a cancellation which arises in a long wavelength limit.
See. Okay, thanks.
Okay.
So if assume that we add some sort of random disorder to the model, is this line disappear or still arise?
We didn't check that, but probably random disorder will destroy this effect.
Thank you.
At the middle of your presentation, I think I heard that the persistent homology is able to kind of maybe distinguish, like classify quantum entanglement, and I was curious how it could be used to classify it.
So you're referring to this one? Yeah,
Yeah.
so in this case, the input data, you have these, say, multi-qubit states, and then the authors, as a distance measure, introduce the pairwise entanglement between the different qubits. So, so this classification is based off the pairwise entanglement of your state.
I was curious that, like, when you input the data, like, because it's too high dimensional, you have to kind of reduce it, and maybe the entanglement kind of changes. So I was curious if it.
So if I recall correctly, in this paper, they were considering various dimensions. Like they started with 3 qubits and they go up to, say, 10 qubits, and as the dimension of your system is increasing, they obtained more classes of entanglement.
Oh, I see. Thank you.
Yeah, please.
You mentioned that, okay, you showed us that unsupervised learning has some features which are making it more interesting than supervised learning. But then again, there's also the choice of the metric, which you highlighted a few times. So that kind of is, well, it's not a supervision act, but it is kind of like restricting what will come next. Is there some way of classifying different types of metric choices and maybe even scanning through most of the different classes so that you can make sure that you will not lose one of these interesting possible the results, as you showed at the very end in this extended Aubry-Andre chain study?
Yes, in practice, for these techniques, you typically have a parameterized metric, and then during this process, you will optimize the parameters to get the best performance. So, for example, yeah, here. So, in this, in both of these metrics, you have this characteristic scale epsilon, which the authors here, they optimize to get the best performance.
Okay, so any other question? Okay, so if not, let's thank the speaker once again. Thank you.